Okay, so let's continue on to our second topic, which is on writing solutions using rref. So we'll start with a theorem. This is theorem 1 from chapter 1. It says each matrix is row equivalent to exactly one rref matrix. So what this allows us to do is to put a matrix into reduced echelon form to solve it. So using this theorem, row equivalent matrices have the same solution. This is what we talked about last time. So we put a matrix into rref to find this solution. There's an infinite number of matrices that are row equivalent, but the one that will give us the solution most clearly is the rref matrix. You can see from just reading this as a set of equations that this is a very simple set of equations. It very quickly tells us what the solution set is. So chapter 1, theorem 1 is super important for finding solution sets. Let's look at an example of this. So let's say we have a matrix that looks like this when it's put into a reduced echelon form. So turning these into equations, we have x1 equals 1. Remember these entries, these first three columns correspond to variables, and then the last column corresponds to the right hand side of the equation. So we'll have x1 equals 1, x2 equals 2, and x3 equals 1. So if we get a matrix in reduced echelon form and it has this nice diagonal of 1s, then we just read off the right hand side and that's the solution set. That's the most simple kind of solution. Let's look at a slightly more complicated scenario. So let's say we put it in reduced echelon form and we have this matrix with a row of zeros. Now this is much like the one that I did earlier. Let's turn this into equations. So we'll have x1 minus x3 equals 0. We'll have x2 plus 2x3 equals 2, and then we'll have 0 equals 0. This one we don't have to report. And we can simplify this a little bit more. So we can write this as x1 equals x3 and x2 equals negative 2x3 plus 2. And then x3 is anything it wants. This can be anything it wants to be. And we call this x3, when we don't have a constraint, we call this a free variable. And we call x1 and x2, because they depend on x3, we're going to call them basic variables. So x3 is our free variable. And sometimes we'll replace our free variable with a parameter like t. So we'll write x3 as t, and then we'll relate everything to that t. So something like this. And we'll talk more about this later on. But t is our parameter here. It's let's use blue. T is our parameter representing our free variable. And this allows us to put this in vector form. We'll talk more about that later. Okay, so the last matrix that we'll consider is this matrix, 1, 0, 1, 0, 0, 1, 2, 2, and 0, 0, 0, 1. And this is something we've seen before. The first two equations are going to be similar to the equations that I got from B, But I'm just going to focus our attention on this last equation, which if we turn into, if we write it out, is saying 0 equals 1. So what this means is that there's no solution to this system. So if we get a reduced echelon form where the reduced echelon form matrix has this bunch of zeros and then a number, a non-zero number, we know that the equivalent system, the system that this is representing, has no solution. All right, let's look at another example. Let's put a matrix. This is a fairly straightforward matrix here. Scroll down a little bit. Into reduced row echelon form and write out the solution set. All right, so let's first get rid of this 2. So if we do minus 2 times row 1 plus row 2 is my new row 2. I'll get 1, 0, 1, 0, 0, 0, 1, 1, and then the last row is unchanged. And then we do minus 3, row 1, plus row 3 is my new row 3. Once you've done these row operations as much as I have, it starts to become second nature. I say that, I'm going to make a mistake. All right, so we're almost done. We have this leading 1 here, and we have to kill the 1 above it. So we'll do minus 1 R2 plus row 1 is my new row 1. And that will give me 1, oops, it's a bad one. 1, 0, 0, negative 1, 0, 0, 1, 1, and then a bunch of zeros. All right, so we have it in reduced row echelon form. Now we turn these into equations. So we have x1 equals negative 1. We have x3 equals positive 1. And we have no information about x2, so x2 is our free variable. And we could write it like this: x1 equals negative 1, x2 equals t, it could be anything, and x3 equals 1. So that's a nice way of writing the solution set. And this has an infinite number of solutions, going back to what I was talking about earlier about you can have 1 or none or an infinite number of solutions. This has an infinite number of solutions. It's a line of solutions.